Good morning, students. Today we are going to see the theorem root 2 is not a rational number. So see the proof. So see the first sentence carefully. Suppose that root 2 is a rational number. See what we have to prove? We have to prove that root 2 is not a rational number. So for that proof, the first sentence we assumed just opposite to the statement. Root 2 is a rational number. So we assumed root 2 is a rational number. So if it is a rational number, it should be in the form m by n. It should be in the fraction. So it is in the form of m by n. Here we assumed where m and n are positive integers with no common factor greater than 1. This condition is very important. Here m and n are we have taken only positive integers with no common factor greater than 1. So that means except 1, there are no other positive numbers are common to both m and n. That means suppose if you take m is equal to 4. If you take m is equal to 4 and n is equal to 2. So what is the common factor between common factor of 4 and 2? It is 2. So here we for root 2 we have taken there is no other common factor except 1. So 1 தவிர அந்த mக்கும் nக்கும் வேற எந்த common factorம் இல்லை அப்படின்னு we have assumed. Okay, so we'll see that you just consider this root 2 is equal to m by n. You're just squaring on both the sides. So root 2 the whole squared is equal to m squared by n squared. So root 2 the whole squared is what? It is 2. So the denominator n squared, when you take it to the left side, it is 2n squared is equal to m squared. Okay, so which implies from this sentence we conclude that m squared is even. Why? So here it's this number m squared is equal to 2n squared. So it's a multiple of 2. So any number is a multiple of 2, it is nothing but even. So m squared is even. If m squared is even, you can very well say m is even. Okay, for example, m squared you will take 16. 16 is a even number. So what is m? M is 4. What is 4? 4 is also even. So m squared is even means m is also even. So m is even means you can take m as multiple of 2. So that's why I have taken here m is equal to 2k. So this m is equal to 2k has to be substituted in 1. So 1 implies what is in the left side? 2n squared, which is equal to, in the place of m, what we have substituted? 2k the whole squared. So 2n squared is equal to, when you square, it is 4k squared. And this 2 and this 4 getting cancelled. So we got the result n squared is equal to 2k squared. Here also some number is multiplied with 2. So we conclude n squared is even. If n squared is even, n is also even. You see the sentence m is even and n is even means m and n are multiples of 2. Okay, so m and n are multiples of 2 means they both have the common factor 2. Okay, so what we have taken for m and n, we don't have common factor except 1. So what we have arrived, m and n having the common factor 2 now. So we arrived at a contradiction. So contradiction means just opposite to what we have taken. What we have assumed, m and n are positive integers with no common factor greater than 1 we have taken. Now what we arrived, m and n having the common factor 2. So it is a contradiction for our assumption. So before that, why we have taken like this? We have assumed root 2 is a rational number. So we arrived at a contradiction. So we conclude that root 2 is not a rational number. So root 2 is not a rational number. So from this theorem, so we can say there are some numbers in the number line, they do not correspond to rational number. So those numbers are named as irrational numbers. So here we introduce irrational numbers. It is denoted by the symbol Q dash. Q is a rational number. Q dash means it's a irrational number. See, yesterday I have said the decimal representation of rational number. So how it should be? It should be, the decimal representation should be terminated. If it is not terminated means they should have the infinite periodic decimals for the rational number. But here the irrational number, the decimal representation of an irrational number will neither be terminating nor infinite periodic. Okay. So you see that irrational number symbol is Q dash. So the union of rational number and the irrational number are nothing but real numbers. It is denoted by the letter R. And it's very clear that the intersection, the common between the rational number in the irrational number is pi. There is a null set. Okay. So from the number system, so first number natural number, next one is a whole number, and the third one is a integer. Next we have seen rational number and irrational number and the real number. So from all the numbers set, we can conclude natural number is it's a subset of whole number. Whole number is a subset of integer. Integer is a subset of rational number, and rational number is a subset of real number. Now we are going to see the exercise 2.1. First question, classify each element of the set root 7, minus 1 by 4, 0, 3.14, 4, 22 by 7 as a member of n, q, r minus q or z. So n means it's a natural number set. Q is a set of all rational number. Then what is r minus q? R is a real number. From that, if you subtract the set q, q is a rational number. So r minus q is nothing but the irrational number, that is q dash. And z symbol is, it's a set of integers. I'll take the first number root 7. What is it? Root 7. Root 7 belongs to, root 7 is an irrational number. So it belongs to the set r minus q. Otherwise you can write it belongs to q dash. And come to minus 1 by 4. So it is in the fraction. So it belongs to rational number, that is q. It belongs to q. Come to 0. 0 we can very well say it is an integer. So it belongs to z. As well as we can write 0 as 0 by 1, 0 by 2. So it is in the fraction form. So we can say 0 is a rational number. And 3.14 it's a rational number. Okay. And 4 is a, you see that 4 is, we can say it's a natural number. And we can say it belongs to the set integer, and we can say 4 can be written as 4 by 1. So we can, it is in the form of m by n. So we can very well say it is a rational number. And what about 22 by 7? 22 by 7 is in the fraction. So it is a, what is that? Rational number. So it belongs to q. Okay. See the second question. Prove that root 3 is an irrational number. Already we have proved, we have seen the theorem, root 2 is not a rational number. The same method we are going to follow to prove root 3 is a irrational number. Suppose that So first we have to assume just opposite to the statement given. So suppose that root 3 is a rational number. If root 3 is a rational number, it has to be written in the form of m by n, where m and n are positive integers with no common factor other than 1. Except 1, there is no other positive integers or common to m and n. Then you consider this relation and squaring on both the sides. So you will get 3 is equal to m squared by n squared. If you multiply n squared to 3, it is 3n squared is equal to m squared. Here you just that m squared is equal to 3n squared. So we can very well say m squared is a multiple of 3. If m squared is a multiple of 3, we conclude m is also a multiple of 3. For example, m squared, you take 36. 36 is a multiple of 3. Then what is m? M is 6. So 6 is also a multiple of 3. So m squared is a multiple of 3. Hence m is also a multiple of 3. So m is a multiple of 3 means m can be written? M is equal to 3k. Okay, so this 3k you have to substitute in the first equation. So first equation implies the left side what you are having 3n squared, which is equal to, in the place of m you are going to substitute 3k. So it is 3k the whole squared. So when you square, 3 squared is 9 and k squared is k squared. So 3n squared is equal to 9k squared. So this 3 and here from 9, if you cancel 1 3, you will get n squared is equal to 3k squared. So from that, which implies that n squared is a multiple of 3. So we'll get n is also a multiple of 3. So here what we have seen, m is also a multiple of 3. Here we arrived n is also a multiple of 3. So both are multiples of 3 means they have the common factor 3. So what we have taken first, except 1, there is no other common factor for m and n. So here we arrived at a contradiction. So our assumption is wrong. So what is our assumption? Root 3 is a rational number. So hence we conclude root 3 is an irrational number, or we can say root 3 is not a rational number. So finally we conclude root 3 is an irrational number. Come to the third problem. Are there two distinct irrational numbers such that their difference is a rational number? Justify. You see, are there two distinct irrational numbers such that their difference is a rational number? So first we have to consider two irrational numbers. So I'll consider a plus b root 2. So root 2 is multiplied, so it is a irrational number. And the next number, how I have considered c plus b root 2. These two are irrational numbers. So in this number, your a, b and c, they are rational numbers. So for example, we can write it is 2 plus 5 root 2. So another number we can say 5 plus 5 root 2. Okay, you can consider like this. Okay, so here 2, 5, this 2, 5, they are rational number. So here I have mentioned a, b and c. They are rational number, but a plus b root 2 is a irrational number and c plus b root 2 is also a irrational number. So here what is asked? Their difference. Then you have to subtract those two irrational numbers. Okay, just consider the first irrational number a plus b root 2 minus c plus b root 2. Okay, so the minus you have to apply to both the terms. So minus c minus b root 2. So plus b root 2 and minus b root 2 getting cancelled. You are getting the answer a minus c. Okay. So the subtraction of the difference of two rational numbers is again a rational number. So therefore a minus c is a rational number. So we conclude there are two distinct irrational numbers in such a way that their difference is a rational number. Okay, thank you students.